Hi everyone, we're going to go over the transfer process for radiant energy. That transfer process is radiation. It is actually probably the most important energy transport process because it transfers energy not through molecules and not through solids or liquids, but it transfers energy via particles and through space. So it's very different, and we're going to go over a few things about it so you can understand how the sun's rays impact us and transfer energy. Whereas before I told you about analogies of communicating with classmates, and I said that conduction was a way of taking kinetic energy and passing a note to your friend, and that convection was actually moving a little closer to your friend, but not having direct contact through a note, but talking to them instead. Well, radiation as a form of moving kinetic energy is like sending them a text, all right? So it goes through the air. I'll give you another analogy. Walking to the beach at the shore, okay? Conduction is when you get to the sand and it's just too hot to walk on because the molecules from the sand are in direct contact with your foot, and that is moving molecules directly from the sand to your feet. Very, very hot, too hot to walk on. Convection is when you feel the hot air coming off the sand. That's different. That you may be wearing flip-flops on the sand, and the flip-flops, especially because they're rubber, they don't conduct well, but you still feel the hot air around your feet. That's the convection, especially the hot air that's right around your knees, because it's above the conductive zone that we've talked about. And the conductive zone is anywhere from the ground surface to about 6 or 7 inches above the ground surface. That's all that air can conduct in. The rest is really convection in the air for ways of moving air temperature around, and we're going to talk about moving air temperature around with radiant energy as well. When we talk about radiation and this analogy, it is really feeling the warmth on your skin. That's what the radiant energy does. It is converted to thermal energy when it strikes your skin. Let's talk a little bit more. Radiation and the movement of particles. Remember, radiant energy is a kinetic energy because it involves movement, and it involves movement of particles rather than molecules. Particles are part of molecules. In fact, they're the photons, but they're not molecules themselves. So radiation, it happens at the speed of light. The photons move in the speed of light. And there are 4 processes that move these packets of photons from the sun through the atmosphere to the earth. And the 4 processes are summed up as 3 delivery processes and 1 return process. So 3 coming in, 1 going out. The 3 that come in amount to reflection, so that you know that you try to reflect as much solar energy away to keep your house cool. You use awnings. Maybe you use a tin roof instead of a regular roof to try to reflect energy to keep your house cool. Sometimes in a car, you might put up a visor in front of your car in the windshield to keep your car cool and to reflect solar energy back out. So there is reflection for radiant energy. There is also transmission, and this brings to mind the car. This is the reason why there are child deaths in the cars on hot days, because glass is such a good transmitter of radiant energy. So much goes right through glass, especially if you have dark seats that are really absorbing the radiant energy. That car can heat up so much more quickly than the air that is convecting around the car. So you're learning more about these processes and how they fit together. And transmission is the issue with car glass and with any glass. And it's what people don't really understand. They don't understand how the car can get so hot. They think it's because the car doesn't have ventilation. So if we put down the windows a bit, we'll have more ventilation. Not enough, because the convection does not overcome the power of the transmission through the glass. Now you can understand a little bit more about that. Absorption is just taking in on those hot seats. You know about absorbing. Black materials absorb the radiant energy, the photons of waves. Emission is what we give off. Remember, first law of radiation. You emit every day, 24/7, 365. Emission is what you give off rather than what comes in. Here is a, sorry about that. Let me go back. Here is a reflection chart that looks at the reflective ability of different materials on Earth. And as you see up there, fresh snow has great reflection on it. And in fact, you notice here that fresh snow can reflect up to 90% of sun's rays. That's why you get a sunburn when you go skiing or when you're out sleigh riding in the middle of the winter, because of all that reflection that comes right off. Clouds are a very important source of keeping Earth cooler, because they reflect incoming solar energy. When we talk climate change, we're going to be talking clouds and their reflectivity, and what kinds of clouds reflect more than other kinds of clouds. Now, in terms of one of the other processes, absorption, and we're going to compare that to emission. When we talk about absorption, we talk about like a really stacked up pizza. That think of the pizza as the ground on the Earth, and think of a pizza with everything on it as being able to accept everything that comes at it, so that a good absorbing material like black soil can absorb all the rays coming in from the sun really well, kind of like a stacked pizza. A pizza with the works can take in all different kinds of solar energy, from ultraviolet to visible light to infrared to all the way out to radio waves. A perfect absorber. And you can have a perfect emitter. Everything that the body takes in, the black soil takes in, they can give off. This picture here is kind of like if you had a vacuum that was sucking everything off of the perfect absorbing pizza. It would just emit out. So what we absorb in during the day could be emitted out all the time, and especially at night. That's a perfect emitter. A black body is an object which can absorb in an enormous amount, an enormous spectrum of the sun's radiant energy, and can emit just as much as it takes in. Absorbs as much as it can take in at the same time. Let me give you an example. A black road is a very close, perfect example of a black body. We'll get into that just a second. But you see here, you know that a black road gets so hot during a hot day. And it gets so hot that you can see the infrared waves coming off of the black road that cause that mirage surface, because they impact on visual light rays that you can see. There's so many infrared rays that are being emitted by the black body. Remember, black bodies can take in a large spectrum, but in general, they, like the Earth, emits out the spectrum that is the lower energy spectrum of infrared, because they can take in a large spectrum, and then they will generally hold a lower temperature that will emit out the longer wavelengths. If you need to go back to the radiant energy video, you'll help to understand the difference between the sun's temperature and the Earth's temperature, the sun's emission and the Earth's emission. This is a pretty good black body. As I said, the black road will take in visible light and infrared light, but it generally will emit infrared light much like the Earth, takes in some visual light and a lot of infrared light, but really emits only infrared light out. Now, one thing to remember is the black body, the black road, is taking in all day long and emitting all day long. And then the sun goes down and it no longer takes in those rays from the sun, but it still continues to emit. So that at night, I want to move this up. What you're noticing here is that by dawn, the asphalt is actually cooler than the ground around it because it has emitted so much more so well. It is a perfect emitter. When you go out at dawn on the black road that was so stifling hot at 3 a.m. the day before, you go out at dawn and that's cool to your feet. It's cooler than the ground because it emits better. Now, I want to compare that black body that you know, the black body of the black road, to the Earth without an atmosphere. The Earth without an atmosphere would emit just as much as came in from the sun. That is why we say that if the Earth did not have an atmosphere, we would be emitting out so much infrared that the temperature on Earth would stay at 0 degrees Celsius, 0 degrees Fahrenheit, stay at freezing because we do not have an atmosphere to hold any warmth in. The Earth would be a black body. That should tell you that a black body doesn't need to be black. It just needs to emit as much as it takes in. It doesn't hurt that it's black, especially when there's only 12 hours of sunlight to feed into the black body. And that's part of the reason why an Earth without an atmosphere can bring in and emit as much as it takes in without an atmosphere. So it doesn't need to be black, it doesn't hurt, but it doesn't need to be black. I went over that. Takes in as much as it lets out without an atmosphere. But with an atmosphere, it's a different story. With an atmosphere, we have greenhouse gases that we critically need to keep life on Earth more moderate. If we didn't have greenhouse gases, we would be frozen and we would not be here. Life would be unsustainable. So we definitely need greenhouse gases. We need just the right amount. We need to maintain a state of radiative equilibrium where we take in as much as we give off, but we take in less than what the sun is trying to get through the atmosphere. We take in less because a lot of that reflection, and then we give off just as much. We are trying to stay in a state of radiative equilibrium. That state is impacted by the 4 processes that we talked about, impacted by the reflection, which helps us take in less solar energy to begin with. We do absorb quite a bit of solar energy, and we do transmit solar energy, which is not absorbed, and we do emit vast quantities of infrared energy. That's the end of what we're going to talk about for the general overview of radiative transfer. Next lecture, we're going to get into the meats and bones of that greenhouse effect.